Okay. Hi, everyone. Thank you for being patient with me. I had to set that poll up, and my poor little Linux laptop is not set up to use Zoom at all. So today we're going to be talking about x86 assembly. This is going to be kind of a crash course in introductory timers, because a lot of the meetings that we're going to do coming up, which is like x86 reverse engineering and phone binary exploitation, requires that you have some familiarity with this. It's not strictly required, but it's very easy to look at a bunch of the assembly and go, oh, I don't know what's going on. So the goal of this is to kind of explain to you how a processor executes a program and how we use assembly to get our human readable abstraction of execution. So announcement, I didn't put anything special. We are currently doing Maple CTF and Buckeye CTF right now, and they both end at 7 p.m. I think we're currently first in the undergraduate division for Buckeye, and we're doing okay to well in Maple. All right, that's the meeting slide. SIGPwny, I'm in the minds of Linux. I'm going to give you a minute to submit that and enjoy me chitting on Emacs for one more time. Okay, so what is assembly? Assembly is a human readable abstraction over machine codes, because at the end of the day, binary has to be operated on by the processor. And the people who have designed these processors have organized bytes in a way that makes sense for instructions and whatnot. And it would be very inefficient to read binary and be like, ah, yes, this is an add instruction. So we can kind of use a bit of text processing to get it down to a readable mnemonic and operations and our variables that we're using, which is good for us, but still quite in an arcane syntax. But if you consider just a simple C function, every time you use GCC or Clang or your favorite compiler, it will bring it down to these assembly instructions, and each of your lines in C does correspond to a certain grouping of assembly instructions. Things get a little bit more complicated when you have loops and if statements and whatnot, but generally speaking, there's usually some boilerplate for function enter and exit, and then any of the actual operations you want to do. So there are kind of three main structures we're going to talk about with respect to how a processor operates on data. There's the instruction memory, which stores all of the assembly that we're interested in executing. There is the registers, which on a 64-bit processor in x86, there are 16 main work registers, and then a couple extra stuff that's used for other things. And then, of course, the stack, which helps manage our program frames and how we return and enter functions. To start, I'm going to talk about instruction memory because it's kind of the simplest. It's just a contiguous block of memory that stores all the bytes corresponding to the instructions of our program. That is it. Normally, that memory is only given read and execute permission. So you don't want your programs to be able to write itself more code in the middle of execution unless you explicitly tell it to. This is stored at a very low address space. So usually we talk about stack being very high addresses and heap being very low addresses. The instruction memory is even below the heap. And finally, it's pointed to by the RIP register. This register is the only register that kind of operates around the instruction memory and can tell the processor what to execute right now. Then we have the registers. So the registers is what we're interested in working with most of the time. They kind of act like variables. They are 64 bits wide, and all they do is hold numbers. They have no semblance of what a type is. They don't know what strings are. They don't know, your favorite linked list node class. They're just holding 64-bit numbers, and we can do all of our computation with all these registers. Most of the registers can be used for whatever you want in a function. If you're handcrafting it, when you compile it, most registers kind of have a purpose that they're usually used for. Two that you really don't want to muck around with too much is called the stack pointer and the base pointer register, which is RBP and RSP. And there are, when writing assembly, there are like lower addressing naming. So if you only want to address the lower 32 bits of the register, you can use this table to know which like addressing scheme to use. So if I have a 64-bit number, RAX addresses all 64 bits, but the AL mnemonic only addresses the last bytes. So this is the whole table for everything. I put at this last row RX like DWB. That's because in x64 it adds the registered 9 through like R9 through R15. There's no like special naming to them. So from there, now that we kind of understand what we're kind of working with variables and what we're kind of working with instruction memory, all of our functions operate on the stack. The reason we're not talking about the heap is, again, from the ISIC processor, all it is pointers to data. The stack is where we're managing our execution of the program. The heap is just data that we're storing in between. So the stack is the region memory located for function, return values, and local variables. So whenever you call a function, it's going to store onto the stack the address of the next instruction, and then it will go and jump to the function that you called. This way, we can go through all of our functions code that we called, and then we can use the saved return address to go back to our callee's instruction like pointer location. Usually you push to the stack to add data and pop to from the stack to remove data. The stack starts at a very high address, so allocating stack is decrementing the stack pointer. As I mentioned before, there are two registers to managing the stack. We have RSP, which acts as the pointer to the top of our stack. Whenever you call all like push or pop instructions, this will decrement or increment RSP. And then RBP is kind of a little bit of a weird one. It stores the base pointer of our stack frame. So every time you call a function, it's going to now consider the next, anything newly allocated is for that one function. And if we call another one, we kind of need to remember where the stack was relative to our original function. So we use this base pointer to keep track of which stack frame is for which function. And so we'll be like saving those along the way with return pointers. So every time we call a function, we say where we are in the stack and where we are in instruction memory before going into the next function call. So yeah, this is kind of a diagram of how you might set up a function call. So any arguments that need to end up on the stack, usually when you're talking about like printf or like really long functions, they'll be on the stack first, and then we push on our return address and then our saved base pointer. So that is where RBP gets set to when you call a function. And then we reserve any memory for local variables. So if I say int x equals 16, I will first allocate out 8 bytes on the stack, and then put in our number, and RSP will point to that top value. And so between the base pointer and the stack pointer, I can address any of my local variables in between, as long as I have some scheme of where I'm laying these variables out. So yeah, in this kind of like simple old example, I've allocated a few numbers, and if the argument is stored on the stack, give you one of the first values, and then I can kind of see how it lays out these values. It isn't always one-to-one with how you code it to how it's laid out in the stack. It's kind of non-deterministic, and the compilers like to maintain 16-byte alignment. So if you just like allocate a like a character value, which is only 1 byte, then it's going to allocate like 16 anyway, and just use the 1. But depending on how you want to pack, characters, integers, and longer types, the compiler will figure that out for you, which can be a stumbling block when you're reversing and exploiting programs. So now it's about time to talk about a note on syntax. When x86 came out, two companies were mainly developing for it: Intel, who made the thing, and AT&T, who made C. So we kind of have this computing standard thing, and when you're browsing on the internet and looking things up, I kind of want to point these two out so you know what to look at and how not to get too confused if the only resource you have is in one syntax and not the other. So Intel says registers as just the register themselves. AT&T places a prefix of a % sign before them. This is just a distinguishing thing for AT&T. It's just more things to write. Immediates, same thing. Intel just gives you the immediate in any assembler. You can use OX to specify hex. Using decimal works too. The assembler will figure it out. AT&T expects you to put a $sign before it. An instruction is laid out in Intel by saying add the destination register is always first, and then any source registers are later. So this adds EAX and BX and saves it to EAX. And notice that these are like different length registers. The processor will figure this out, or the assembler will figure this out on the fly. AT&T, however, AT&T does that. So it adds like command suffixing, which can look really gross. And then comments, Intel uses semicolons to denote comments, while AMD has that familiar C style commenting. So let's talk about basic assembly. Usually every command is laid out with the mnemonic of the command, which you'll probably have to look up in some manual or just kind of get a feel of what they do. Most of them kind of make sense of what you expect them to do once you understand kind of like how assembly uses destination and source registers. So we have like simple examples of like add RAX, BX, and store in RAX. We can use immediates. We can operate on the stack pointer and base pointer. Nothing necessarily disallows us from doing that. It just might make your program crash. A lot of commands that will crash without running anything is if you try to use the instruction pointer register. Usually the only way to control that register is through returning or jumping. This guy, XOR RSI, you'll see this a lot as a compiler trick, because what happens when you XOR a number with itself? What do you get? Zero. So this XOR RSI is a really cheap way to set a byte to 0 because it's faster than subtracting from an immediate or its own register by itself. You have increment values. These guys are shift logical right, left, and shift arithmetic right. If you've taken 233, you kind of know the difference between arithmetic and logical shift. It's just how it shifts bits in one machine word left or right, and whether or not it conserves time. Sometimes you get instructions with 3 parameters. So imul will multiply R10 and an immediate and store the result in R8. And no-op up here does nothing. I believe the actual like true byte is that what no-op is the byte you get when you move RAX to RAX. So it's just doing a move instruction in the same register. Okay. Logic flow. So we like our if statements and go-tos and for loops and all that good stuff. So we can use jump to go somewhere in our instruction memory. A lot of these jumps are relative, but when we're writing assembly and having it be compiled, we can use labels in our code, and the assembler will figure out those relative jumps for us. This is one of the few ways to modify RIP. There's also like absolute jumping, so you could provide a full instruction memory address and jump to that. You can also use call, which will set up return registers on the stack and stuff, so maybe not always ideal depending on the situation. In general use, you like call. The other way we can do logic flow is by testing values. So there's the compare instruction, which will just subtract item A and item B and set a kind of special use register called E flags or R flags. All this flags register stores is the result of the last operation, and some assembly commands will set different flags. Compare, most often than not, will tell you whether or not like if it's 0, if it's non-zero, and you can do all of your like bounds checking by just subtracting and checking whether or not it is equal to, greater than, or less than 0. And so there's this mnemonic of J and then CC, which responds to compare values. There's like 64 possible jump commands you can say in an assembler. So you can say JNZ for jump if not 0, or JZ if jump is 0, or JE if jump if equal. And all these things, shake down to just test two values, jump depending on some condition. I can, build my for loops and my while loops and my if statements from that. So for an example here, we move two values into RAX and RBX as immediates. And then I have this label here called foo. I can compare these two values, and if they're not equal, I can jump to bar, and bar will decrement RBX and jump back to foo. If this jump not equals fails, we just move on to the next instruction. It's all stored linearly, and so if something doesn't tell RIP to move somewhere else, it's just going to move to the next instruction. So then, if once this fails, it will set RAX to 0, and then it will return. Assuming we're in like some nice call frame, this will pop the return address off the stack and then move back to the callee function, or the caller function. Sorry. Using the stack. So using the stack is pretty important because we like saving values. We use push and either a register or an immediate to add something to the stack, and then the processor will automatically decrement the stack pointer register. Pop will pop a value from the stack into the register supplied and automatically increment the stack pointer. So this is kind of what people talk about, that stack is automatic memory management. We don't actually delete anything, we just kind of stop looking at it. So it's still like saved in the virtual memory space. So if you were able to access outside of the range of the stack pointer, you might be able to get old initialized values. So yeah, using the stack, I have a bit of an example here. So at the start of time, we have our stack pointer and base pointer all pointed to the same base pointer that happens when we call this function. And then we move this value into RAX as an immediate. So now RAX equals that small little value. And then we push RAX to the stack. So this will automatically decrement the stack pointer, place that value on the stack. We can 0 RAX if we wanted to. And if we pop RBX, we decrement RSP, and now RBX equals our value. We're replacing whatever it was before. Syscalls. So now that we kind of have an idea of stack instruction memory and like how we kind of do control flow, I'm going to talk about function calling in a way that's more relevant to us in security. So if you want to call a function, you just say call and then the address of the function, which is just some pointer in instruction memory. But there's a series of functions called syscalls, which are provided by the Linux kernel. When you call a syscall, it doesn't actually jump to any code. It will just go to the next instruction in your instruction memory because the syscall happens in kernel space, which is not your program. GOC provides wrappers, but you can call these directly using the syscall instruction. So if you've ever used read, exit, open, or execve before in C, these are all system calls. This is how you interact with your computer directly in a C program. So how do you call a syscall? Well, there's a giant table that is an ID number to the proper syscall. You need to load that number into the RAX register. This identifies which syscall you're trying to call. And I have a link here that lists that table. I also provide other resources to look that up. It's also easy to Google. And then you load your arguments into the register in order. So the first argument of any function, this applies to not just people, is always loaded into RDI. And then you go to RSI and RDX. And then in 64-bit, it automatically uses R10, R8, and R9. If you have more arguments, then that's when you provide a pointer to the stack, and then the program will use the stack addresses to load the additional arguments. And then when any function returns in x86, the return result is stored back in RAX. So that original ID number gets overridden with your return value. So this is a couple examples of setting up syscalls. So if I wanted to call exit 10, I load the ID for exit in just 3C, and I then do move RDI into, I move the value of 10 into RDI, and then I call syscall, and that will exit my program with return code 10. If I want to do something more interesting, like pop a shell, I can move REX OX3B. That gives me the exec.v syscall, and then we'll move like the stack pointer into RDI. So this makes our RDI point to the same address that the stack pointer is pointing to. And let's say, when I did that.
It should be back. Yeah.
Okay, sorry about that. If I have bin sh just located on the stack as a value, then this acts as a pointer to bin sh. So that acts as like a C string. And then I want to zero out the other two values to treat them like null pointers. So then I call syscall. And that will make my program stop running and instead run /bin/sh. And that's how you set these up in assembly to call other functions. Pointers and dereferencing. So, like I said, there's no semblance of types in x86. It's just numbers and links. So everything you eventually are just working with either the numbers of interest in whatever math you're doing, or you have a pointer and you want to reference addresses inside of your memory. So very simply, if you just have the address you're interested in, you can like move the value that address is pointed to into another address by using brackets. But x86 is also nice. We have some values where we can like do some nice iteration. So we can do some math within that bracket. So we can have an index register that stores like what index of the array we're trying to go to, a scale. So we're storing integers, we might need to scale by 4 instead of by 1. If we have a string, we would just leave that as our x. And then a displacement. So if you're iterating through structs, not all of your data is lined up at the exact address. You might have to have a constant displacement off of each memory address. And you can use this as a dereference. And you can use this dereference operator in a lot of assembly commands, not just move. You can use it in compare and math and so on and so forth. I think one thing x86 doesn't let you do is it doesn't let you have the source and destination both be dereferenced. So eventually you have to load one into a register. There's also another relevant command I'll mention here called LEA, which is load effective address. Load effective address will take the value that is computed from this math and move it into the first address you gave it. It does not actually reference any memory, but it's very useful to do that pointer math without actually addressing anything. Yeah, and you can write memory the same way. So if your destination register is a dereference, it will just write to that dereference value. And that's about it. I provide some resources on some slides. I believe you can at least access them from like last year's meeting. If they're not up already, I'll post them in Discord as well. I provided you the manual, a manual of x86. It's kind of arcane to read. However, if you are confused about what any command does, it's very like just you can try reading it and see if you can get a better intuition into what it's doing. This manual usually provides like pseudocode for what that assembly instruction does, and it tells you what types of parameters you can use. So sometimes it's an immediate, sometimes it's a register, sometimes it's only a 32-bit register, and so on. I have an online assembler link that you can go to. This allows you to write some assembly in a text box and assembles it to a byte string that you can use in like Pro Tools or Echo or Python and so on. There's the Chromium docs, which is like the syscall table and argument convention, and there's a couple other like resources to like mess around with assembly. Some challenges. I have 5 challenges up. They've been up on the vault for a while, but if you want to take a crack at them now, they should be available in like the actual like meeting list challenges. So the easy ones I would say is ADSM adder and lever. This just requires you to do a bit of like math and assembly. Then I have some harder ones, which is reader and shellcode, and then the hardest one, which is modifier, which requires a bit of trickiness with actually understanding that your code is just data and you can write data in executable sections. Code tools. you can link up to the challenge with process and then send the line with your shellcode. They'll always just expect shellcode and then move on. There's no fancy tricks or like huge parsing you need to do when you do these challenges. If you have trouble with code tools, let me know. I will try to help you. I know it's a pain on Mac. At the end of the day, you can always use the online disassembler and then just send in your string via like echo. Meetings next, this upcoming Thursday, we're talking about Rev 2 now, which we'll talk about x86 assembly. And then next Sunday, I believe, is a meeting of circumventing DRM with OGIS. So please come to those meetings. I believe that is it. Yeah, so if you have any questions, feel free to ask me, tackle on all those problems. I'm here to help. I'm sure I can drag other people to help as well. So yeah,